Okay, let's unpack this. Today, we are diving deep into something absolutely fundamental, something that is literally at the core of everything we interact with. The atomic nucleus. Forget the headlines about power plants or bombs for a second. What is nuclear physics really about? It's a journey to understand the heart of matter itself, the tiny, dense packages of protons and neutrons that dictate the universe around us.
That's right. It's about these incredible miniature systems that hold atoms together and, in doing so, are responsible for everything from the energy that powers the sun to the very elements that make up our bodies.
Yeah. And we have a fantastic stack of sources to guide us on this deep dive. We're
Yeah.
working from excerpts of a physics textbook that lays out the landscape, starting with the absolute basics, what a nucleus is made of, the weird forces at play,
Yeah.
and taking us all the way through how these things live and die, react with each other, and even where the elements themselves came from.
Our mission today is, well, to navigate this often dense material for you. We want to pull out the most fascinating, the most important, and maybe the most surprising insights.
Right.
We want to show you what makes nuclei tick and, understand why this seemingly obscure field of physics has such massive real-world implications.
And get ready for some incredible connections. We're talking about how understanding the structure of something less than a trillionth of a millimeter across, it's tiny,
Incredibly small.
can help explain massive cosmic objects like neutron stars and reveal the history of the elements that literally surround you right now.
It's a remarkable link between the quantum world and the cosmos. It really is.
Absolutely. So let's jump right in. What is a nucleus at its core? What's rattling around inside? What is the glue that holds it together? And what are some of its most basic features?
Okay, so at its heart, a nucleus is what we call a quantum mini-body system. Think of it as a tiny, complex dance floor filled with particles called nucleons.
Nucleons, right? Protons and neutrons.
Exactly. Those are the familiar protons and neutrons. And they're held together by an incredibly powerful interaction we call the nuclear force, or sometimes the strong interaction.
Okay, so protons and neutrons are the dancers. But are they simple little hard marbles? I remember learning that even they have internal structure.
That's a crucial point. No, they aren't structureless. A key piece of evidence for this comes from their magnetic properties. Protons and neutrons have what we call anomalous magnetic moment.
Anomalous, meaning unexpected.
Exactly. If they were simple fundamental particles like electrons, their magnetic signature would be predictable by a theory called the Dirac equation. But they deviate significantly from that prediction. A neutron, for example, despite having no net electric charge, even has a non-zero magnetic moment.
Wow, okay.
This deviation, well, it screams that they aren't elementary points. They're composite particles with internal structure made up of even smaller things like quarks.
So these structured protons and neutrons are glued together by this strong interaction. How does that compare to, say, the electrical force that makes, like, charges repel?
Oh, it's vastly different and much more complex.
Yeah.
The Coulomb force, the
Mhm.
electrical one, is relatively simple. It just depends on the distance and the charges 1 over r squared kind of thing.
Right.
The nuclear force, however, is deeply dependent on properties of the nucleons themselves, like their spin and something called isospin.
Isospin?
Yeah, it's kind of like a quantum label, distinguishing protons from neutrons in terms of how they feel the nuclear force. This complexity is why understanding the nucleus is such a challenge.
Are there any other fundamental forces that play a role in the nucleus? I mean, besides the strong one?
Yes, definitely, though their influence varies.
Yeah.
The weak interaction is absolutely essential for nuclear decay, specifically beta decay. That's where a neutron can turn into a proton, emitting an electron and an antineutrino.
Okay.
It's also key in certain processes that build elements beyond iron. And the electromagnetic interaction, the Coulomb force we just mentioned, is critical for the protons, causing them to repel each other, constantly trying to tear the nucleus apart.
So the strong force has to overcome that repulsion.
Precisely. It has to win that battle.
What about gravity? We know gravity is important for big things. Does it matter inside the nucleus?
For the structure of a typical atomic nucleus, gravity is incredibly weak compared to the strong and electromagnetic forces. It's essentially negligible. You just don't need to worry about it there.
Okay.
However, you see its dramatic role elsewhere, like in holding together massive neutron stars, which are, in some ways, like gigantic nuclei, or in the extreme conditions required for certain types of nucleosynthesis. So important cosmically, but not usually for individual nuclear structure.
Got it. If we wanted to see a map of all the known nuclei, how would we do that? Is there like a periodic table for nuclei?
Sort of. We use the nuclear chart, or sometimes called the Segre chart. It's basically a plot where you count the number of neutrons, N on one axis, and protons, Z on the other. Each box represents a specific nucleus.
And the stable ones, where do they sit?
The nuclei that are stable, the ones that don't decay spontaneously, form a relatively narrow band, often called the Valley of Stability. There are only about 256 stable nuclei known. For lighter ones, they tend to have roughly equal numbers of protons and neutrons, so they sit near the diagonal NEZ line on the chart.
And the sources mention some pretty exotic types of nuclei being explored. Sounded interesting.
Yes, like hypernuclei.
Yeah.
These are truly novel because they contain particles other than just protons and neutrons specifically, particles that contain strange quarks, like lambda or sigma particles. Studying them really pushes the boundaries of our understanding of how these strange particles interact within a nucleus. It's frontier stuff.
Okay, so we've got protons and neutrons inside, held by this complex nuclear glue. Let's talk about the nucleus as a whole entity. How big is it and how dense is it? What are its sort of bulk properties?
Right. This is where the very first simple model of the nucleus emerged, the idea of it being like a liquid drop. Basic bulk properties, like its overall size and mass, hinted at this simple picture initially.
And how do you even measure something that small? We're talking femtometers, right? 10 to the minus 15 meters.
Exactly. Incredibly tiny. Early experiments, like Rutherford scattering alpha particles off atoms, gave us a rough idea of the nucleus's size. They saw how the alpha particles were deflected. The pattern looked a bit like Fresnel diffraction, caused by the strong electrical pushback, the Coulomb repulsion, and also the nucleus sort of absorbing particles that got too close.
But we have better ways now.
Oh, definitely. More precise measurements, especially of the proton distribution, use high-energy electrons. Electrons interact electromagnetically, so they primarily see the protons. Because nuclei are so small, you need electrons with very short wavelengths, which means high energy.
High energy to get good resolution, basically.
That's exactly. Analyzing how the electrons scatter, using something called the form factor, lets us map out the charge distribution pretty accurately.
Is there a standard way to mathematically describe that size and shape? Like a formula?
Yes. The Wood-Saxon representation is a widely used functional form to describe the density distribution. It's got parameters like a radius parameter r and a surface diffuseness parameter a, which tells you how thick the edge or the skin of the nucleus is. It's not a sharp cutoff.
It gets fuzzy.
Bit fuzzy, yes. And a key finding from these electron scattering measurements is that the radius r is proportional to the cube root of the mass number a. So r goes like a to the 1/3 power.
And that r proportional to a to the 1/3 relationship is the evidence for the liquid drop model. How does that work?
Precisely. If the radius goes as a to the 1/3, then the volume, which goes like r cubed, must go proportionally to a itself.
Ah, right. Volume proportional to the number of nucleons.
Exactly. And since the mass is also roughly proportional to a, the number of nucleons, this means the density mass over volume ends up being roughly constant across almost all nuclei. It's about 0.14 to 0.17 nucleons per cubic femtometer. That constant density is exactly what you'd expect from an incompressible liquid drop.
Okay, so that's the proton distribution from electron scattering. What about the neutrons? How do we see them?
Yeah, measuring the total mass distribution, which includes the neutrons, is harder. It requires using probes that interact via the strong nuclear force, not just electromagnetism. So things like scattering protons or neutrons or even entire nuclei off the target nucleus.
Right, because neutrons don't have a charge, but they feel the strong force.
Correct. And what's really fascinating is that in unstable nuclei, especially those far from that valley of stability on the nuclear chart, the proton and neutron distributions can look quite different. You can get phenomena like a neutron halo.
A halo?
Yeah, where one or two neutrons extend really far out, like a fuzzy cloud around a more compact core. This happens in some very light neutron-rich nuclei like lithium-11. Or you can have neutron skin, which is a layer of almost pure neutron matter on the surface. This has even been suggested for a heavy stable nucleus like lead-208. This difference in proton and neutron shapes is a really active area of current research.
That's pretty wild. So we have size, density, and even different shapes for protons and neutrons. What about how tightly the nucleons are held together, the energy aspect?
That's described by the binding energy. You can think of it as the energy you'd need to put into the nucleus to completely break it apart into its individual protons and neutrons. Or, conversely, the energy released when you form the nucleus from scratch.
Okay. And is it the same for all nuclei?
No, and that's crucial. A really important concept is the binding energy per nucleon. Just take the total binding energy, B, and divide by the mass number, A. If you plot this BA value against the mass number, A, you get a very famous curve.
Ah, yes, I think I've seen that. It goes up fast, then peaks, then slowly drops.
Exactly. It rises quickly for light nuclei, then peaks around mass number 56 to 62, right around iron and nickel, and then it gradually decreases for heavier nuclei.
And that peak around iron is incredibly significant, right? You mentioned stellar stuff earlier.
It is. That peak is precisely why iron is often the endpoint of fusion reactions inside stars. Fusing lighter elements up to iron releases energy because you're climbing up that binding energy curve towards the peak, becoming more stable.
More tightly bound.
Right. But trying to fuse elements heavier than iron actually requires you to put energy in because you're moving down the curve away from the peak. This curve fundamentally explains why iron is so abundant in the universe and why massive stars stop their fusion process at iron.
And speaking of energy, this binding energy difference is where the power from nuclear reactions comes from. Fission and fusion.
Exactly. The energy released in any nuclear reaction is simply the difference in total binding energy between the initial nuclei and the final products. For example, fusing deuterium, a proton and neutron, and tritium, a proton and two neutrons, to make helium-4 and a neutron releases about 17.5 MeVs of energy. That's a huge amount per reaction compared to, say, chemical reactions. That's the basic promise of fusion energy.
But fusion isn't easy because those positive protons in the nuclei push each other away really hard. You have to overcome that electrical repulsion, the Coulomb barrier you mentioned.
Right. That's the big hurdle for fusion. The standard approach is high-temperature fusion, basically. You heat a plasma of deuterium and tritium to millions, even hundreds of millions of degrees.
Wow.
Yeah, so the nuclei are moving so fast they have enough kinetic energy to just slam right through that repulsive barrier and get close enough for the strong force to take over and fuse them. That's what devices like tokamaks and stellarators are trying to achieve.
But the sources mention a completely different approach that feels almost like cheating the barrier. Muon-catalyzed fusion.
Yes, muon-catalyzed fusion, or UCF. It's a fascinating alternative. Instead of relying on brute force high temperatures, you use a particle called a muon. A muon is basically like a heavy electron about 200 times heavier.
Okay.
Now, if you can get a negative muon to replace the electron orbiting in, say, a molecule containing deuterium and tritium, because the muon is so much heavier, its orbit is much smaller, much closer to the nuclei.
Ah, it pulls them closer together.
Exactly. It pulls the deuterium and tritium nuclei incredibly close together, effectively shielding their positive charges from each other and dramatically lowering that Coulomb barrier. This allows fusion to happen even at relatively low, almost room temperatures.
That sounds amazing. Has it worked?
It has. It was first confirmed experimentally back in 1956 by Luis Alvarez and his team. They saw bubble chamber tracks showing a muon stopping, triggering a fusion reaction, specifically proton plus deuterium due to helium-3, and then the muon shooting off again with the energy released. The sources we looked at call this approach currently thought to be most promising, specifically for the deuterium-tritium fusion reaction, because of some specific resonances involving muons in that DT system.
That's remarkable, using a different fundamental particle to fundamentally alter the interaction and make fusion possible without needing stellar temperatures. Okay, let's dig deeper into that nuclear force itself, the glue. What more can we say about how it actually works?
Well, the fundamental idea in particle physics is that forces are mediated by the exchange of particles. The range of the force is related to the mass of the particle being exchanged. Heavier particles mean shorter ranges.
Right, like the photon for electromagnetism has zero mass, so infinite range.
Exactly. And the nuclear force was originally linked to mesons by Hideki Yukawa back in the 1930s.
Mesons, like pions.
Precisely. Yukawa proposed that the nuclear force was mediated by particles with masses between the electron and the proton mesons, like the pion. Because these mesons have mass, the resulting force has a characteristic spatial dependence. It's often called a Yukawa-type potential. It falls off exponentially with distance, much faster than the first dependence of the Coulomb force.
So it's strong, but only over very short distances.
Yes, it's a very short-range force. Its strength drops off incredibly rapidly outside the scale of the nucleus, which is why we don't feel it in everyday life.
You mentioned its complexity earlier, like depending on isospin. Can you elaborate on that?
Yes. The nuclear force exhibits some important approximate symmetries. It turns out to be very similar whether you're looking at the interaction between two protons or a proton and a neutron, or two neutrons, if they were in the same quantum state regarding spin and orbital motion. This is called charge independence.
Okay.
And more specifically, the neutron force is experimentally found to be very, very close to the proton force once you account for the Coulomb part. This is called charge symmetry. We see evidence for these symmetries when we compare the energy levels of related nuclei, like mirror nuclei, where you swap all protons and neutrons, or isobars, which have the same total number of nucleons. Their energy level structures are often strikingly similar.
What does the force feel like at different distances? Is it always attractive pulling them together?
No, and that's another layer of complexity and kind of counterintuitive.
Hmm.
While low-energy scattering experiments are gently probing the interaction, suggest an overall attraction that holds the nucleus together.
Which makes sense. You need attraction.
Right. But high-energy scattering experiments, where you really slam nucleons together, reveal something different. If you push nucleons very, very close together, the force becomes strongly repulsive. There's like a hard core.
A repulsive core, so they resist being squeezed too close.
Exactly. So the picture that emerges is an attraction over slightly longer distances, a few femtometers, but with a hard repulsive core at very short distances, less than about half a femtometer. The exact shape of the potential is complex and includes terms depending not just on distance, but also on the nucleon spins, their relative angular momentum, and other factors. It's not a simple central force.
So how do scientists theoretically describe this complicated beast?
Well, historically, the meson exchange models, like exchanging pions, explain the longer-range attraction reasonably well. Exchanging heavier mesons, like the Rho and Omega, helped with shorter ranges. But they struggle to explain that hard repulsive core naturally.
So what are the modern approaches?
Modern approaches get more fundamental. Some look at the quark cluster model, treating nucleons as bags of 3 quarks and seeing how those bags interact. Others use effective field theories derived from the fundamental theory of quarks and gluons, quantum chromodynamics, or QCD, like chiral perturbation theory. And then there are attempts at direct calculations using QCD on a computed grid in space-time lattice QCD, though that's computationally incredibly intensive.
Okay, those sound like fundamental theories. Are there practical models that physicists actually use in calculations of nuclear structure?
Yes, absolutely. These are often called realistic phenomenological potentials. They aren't necessarily derived directly from first principles like QCD, but they are carefully constructed mathematical forms. They include all the necessary complicated terms, central attraction, repulsion, spin-orbit terms, tensor forces, you name it.
Tensor forces.
Yeah, forces that depend on the orientation of the spins relative to the line connecting the nucleons. Very complex. The parameters in these phenomenological potentials are then precisely adjusted or fitted to reproduce the vast amount of experimental data we have from nucleon scattering experiments across a wide range of energies. Potentials like the argon V18 or the Nijmegen potentials are famous examples, and crucially, they all explicitly include that strong repulsive core at very short distances.
Now, you mentioned something important earlier. The force between 2 nucleons inside the dense environment of a nucleus is different from the force between them out in empty space. Can you expand on that?
Yes, it's a critical point. Inside the dense nuclear medium, where nucleons are constantly jostling with their neighbors, the interaction they feel is significantly modified compared to the bare interaction in free space. Think of it like trying to understand how 2 people interact in an empty room versus how they interact crammed into a packed subway car. The presence of others changes things.
Okay, the environment.
Hugely. This modified interaction inside the nucleus is what we call the effective interaction, and that's what we actually need to use in most nuclear structure calculations. There are various ways to derive or model these effective interactions, sometimes using theories like Bruckner theory, or often using simpler phenomenological forms. Forces like the Skyrim force or the Gogni force are very popular examples of these effective interactions.
Skyrim and Gogni.
Yeah, they are designed specifically to work within the nuclear medium, and their parameters are fitted to reproduce bulk nuclear properties like the binding energy, the saturation density, the incompressibility of nuclear matter, and so on. A crucial feature often built into these effective forces, like the Majorana exchange term found in some older forces like the Volkov force, is related to ensuring that the nucleus saturates.
Saturates, meaning it doesn't collapse.
Exactly. It means the nucleus settles at a finite density and binding energy per nucleon rather than collapsing into an infinitely dense point or flying apart. Saturation is a fundamental property of nuclei, and the effective interaction needs to guarantee it. The exchange nature of the force plays a role here.
Okay, so we have the basic structure, the complex glue, both bare and effective, and the overall size and density described by the liquid drop idea. But you mentioned earlier that the simple liquid drop model isn't enough. What phenomena point beyond that simple picture?
Right. The clearest evidence that nuclei aren't just simple uniform liquid drops is the existence of magic numbers.
Magic numbers. Okay, you mentioned those briefly. What are they again?
These are specific numbers of protons and/or neutrons. The main ones are 2, 8, 20, 28, 50, 82, and 126, where nuclei show exceptional stability.
More stable than their neighbors.
Much more stable. They have significantly higher binding energy than the smooth liquid drop model would predict. They're often perfectly spherical in shape, resisting deformation. They also have higher excitation energies for their first excited state, and these magic numbers influence things like how heavy nuclei tend to fission.
So kind of like the noble gases in chemistry, where certain numbers of electrons fill shells and make atoms super stable and unreactive.
Exactly. It's a very, very similar conceptual idea. It points towards some kind of shell structure within the nucleus, analogous to the electron shells in atoms. Shell closure leads to enhanced stability.
But presumably the reason is different, not electron orbits.
The reason is different, and the numbers themselves are different too. 2, 10, 18, 36 for electrons versus 2, 8, 20, 28 for nucleons. In atoms, it's the long-range electrical force from the central nucleus that creates the potential for the electron shells. In nuclei, it's the collective effect of the short-range nuclear force from all the other nucleons, creating an average potential. And critically, to get the correct nuclear magic numbers, you need a very strong interaction called the spin-orbit interaction.
Spin-orbit interaction. Okay, what's that?
It's an interaction that depends on the coupling between a nucleon's intrinsic spin, like a tiny spinning top, and its orbital motion around the nucleus. The energy is different depending on whether the spin and orbital angular momentum are aligned or anti-aligned.
And this is where the nuclear shell model comes in.
Precisely. The nuclear shell model is the nuclear equivalent of the atomic shell model. It's based on the idea that, to a first approximation, nucleons move independently in an average potential, or mean field, created by all the other nucleons. This mean field potential is often approximated by that Woods-Saxon shape we discussed earlier, reflecting the finite size and diffuse surface of the nucleus.
And solving the Schrödinger equation for a nucleon in that potential gives you the shells, and if you include spin orbit, the magic numbers.
That's the key. If you just use a simple potential like a harmonic oscillator or even a basic Woods-Saxon potential without the spin orbit term, you get shell closures, but at the wrong numbers, like 2, 8, 20, 40, 70. It was Maria Guppert-Mayer and J. Hans D. Jensen who realized independently in the late 1930s that adding a strong spin-orbit interaction was crucial.
What does it do?
This interaction significantly splits energy levels that would otherwise be degenerate, have the same energy. Specifically, it pushes down the energy level where spin and orbit are aligned, total angular momentum J equals L plus 12, and pushes up the level where they are anti-aligned, J equals L 12. This splitting is large enough to rearrange the order of energy levels compared to simpler potentials, and it creates significant energy gaps precisely at the experimentally observed magic numbers, 20, 28, 50, 82, 126. It was a huge breakthrough.
And the shell model can predict properties beyond just stability.
Oh yes, it can predict many properties, especially for nuclei that have just one or a few nucleons outside a closed magic shell, or one or a few holes inside a shell. By looking at the quantum numbers, like angular momentum and parity, of the shell model state occupied by these valence nucleons, you can predict things like the ground state spin and parity of the entire nucleus.
Like an example.
For instance, the model correctly predicts that lead-209, cell in P, which has one neutron outside the doubly magic lead-208 core, Z82N126, should have a ground state spin and parity of 92 plus May. This comes directly from the properties of the specific neutron orbit, due to your rho, that the extra neutron occupies according to the shell model level scheme.
Okay, so the shell model says nucleons move independently in an average field, but you've stressed how complex the actual interaction between nucleons is. Is that interaction just ignored?
In the simplest version of the shell model, yes. The model relies on the mean field, which captures the average effect of all interactions. The remaining part of the interaction, the bit that's not captured by the smooth average potential, the direct fluctuating interaction between individual valence nucleons, is called the residual interaction.
And this residual interaction is important.
It's vital for explaining the finer details of nuclear structure that the simple independent particle picture misses. Things like the precise ordering and spacing of excited states, mixing between different configurations, and certain collective effects depend heavily on this residual interaction.
And that pairing effect you talked about earlier, the tendency for identical nucleons to couple to spin zero, is that part of the residual interaction?
Yes, that's arguably the most important component of the residual interaction, especially at low excitation energies. The strong attractive force between pairs of identical nucleons, proton or neutron, when their spins and orbital angular momenta couple to a total angular momentum, J equals 0, is a direct consequence of the properties of the nuclear force, particularly at short range.
Why JGO specifically?
Because the nuclear force is short-ranged, the interaction is strongest when the nucleon's wave functions overlap the most. For two identical nucleons in the same shell, the maximum spatial overlap occurs when they are in time-reversed orbits, which corresponds precisely to coupling their angular momenta to J00. This J0 paired state is significantly lowered in energy.
And that explains the extra stability of even nuclei.
Exactly. It explains why nuclei with even numbers of both protons and neutrons,
Yeah.
even nuclei, are systematically more stable and more tightly bound than their odd A or odd neighbors. It also explains why the ground state of virtually all even nuclei is 0 plus Le, and why the first excited state in nuclei with two valence nucleons outside a core is often a J2 plus state, not the J0 ground state. We saw that example in lead-210 to actual QPP in the sources.
Okay. Does the mean field potential itself care if a nucleon is a proton or a neutron beyond just the Coulomb force for protons?
Yes, it can. While charge independence suggests the nuclear force is roughly the same, there can be subtle differences, and the mean field experienced by a proton can be slightly different from that felt by a neutron, even ignoring Coulomb. This is partly because a proton interacts with Z1 other protons and N neutrons, while a neutron interacts with Z protons and N1 other neutrons. If N and Z are different, the average field might differ slightly. There's a term sometimes added to the potential called lane potential, which explicitly describes this isospin dependence of the mean field.
How are these mean field potentials actually determined in modern calculations? Is it just assumed to be Wood-Saxon?
Well, Wood-Saxon is a good phenomenological shape. More sophisticated calculations aim to determine the mean field self-consistently. A common method is called Hartree-Fock, or Hartree-Fock-Bogoliubov if pairing is included.
Self-consistent, meaning?
It means the potential isn't fixed beforehand. You start with a guess for the wave functions of all the nucleons. Then you calculate the average potential created by those wave functions using an effective nucleon interaction, like Scheimer-Gauge. Then you solve the Schrödinger equation for nucleons, moving in that potential to get new, hopefully better, wave functions. You repeat this cycle. Calculate potential from wave functions, calculate wave functions from potential until the wave functions and the potential they generate no longer change significantly. They become consistent with each other.
I see. And those Scarmi and Gagni forces are designed for this?
Yes, they are phenomenological effective interactions, specifically designed for use in these self-consistent mean field calculations. The Scheimer force is particularly popular because its mathematical form, often involving zero-range delta functions, simplifies the calculations considerably while still capturing essential physics like saturation, spin-orbit splitting, and surface properties. The parameters of these forces are carefully fitted to reproduce a range of known nuclear properties across the nuclear chart.
Are there other approaches besides Hartree-Fock with Schermer-Gagni?
Yes, another important microscopic approach is relativistic mean field theory, RMF. Instead of a potential, it describes the interaction through the exchange of meson fields, like sigma, omega, rho mesons, treated within a relativistic framework. RMF has been quite successful in describing saturation properties, spin-orbit splittings, and phenomena related to nuclear spin that are sometimes challenging for non-relativistic approaches.
And how does pairing fit into these mean field calculations? Is it automatic?
Not always in the simplest Hartree-Fock. The strong pairing correlation often needs to be added specifically. A common way is to use methods borrowed from the theory of superconductivity in metals, like the BCS theory, Bardeen-Cooper-Schrieffer, or its generalization, the HFB Hartree-Fock-Bogoliubov method mentioned earlier. These methods introduce a pairing field or gap parameter, often denoted by U, that represents the strength of this JO0 pairing attraction. Including pairing is crucial for accurately describing the ground state energies, especially the extra binding of even nuclei, and low-lying excited states in many nuclei.
Okay, so we've gone from the liquid drop for bulk properties to the shell model focusing on individual nucleons, magic numbers, and residual interactions like pairing. What about the overall shape of the nucleus? Are they always spherical like the simple shell model might assume?
No, definitely not. That's another key area where the simple picture breaks down. While nuclei at or very close to the magic numbers are typically spherical in their ground state, most other nuclei, the vast majority, in fact, are found to be deformed. They are not round.
Deformed, meaning squashed or stretched.
Exactly. We usually describe this deformation using mathematical parameters, often multipole expansions. The most common type is quadrupole deformation, which corresponds to shapes that are either stretched out along one axis like a rugby ball or American football, that's called prolate, or flattened like a pancake or a discus, that's called oblate.
Correlate and oblate. Okay.
You can visualize these shapes, and there can even be more complex deformations like octupole, pear shapes, or higher orders, but quadrupole is the dominant one for ground states.
Can a nucleus that's normally spherical do anything shape-wise?
Yes, even nuclei that are spherical in their ground state can get excited into states corresponding to surface vibrations. The nuclear surface can oscillate, sort of like a vibrating liquid drop. These can be quadrupole vibrations, oscillating between prolate and oblate shapes around the sphere, or octupole vibrations oscillating into pear shapes, leading to characteristic patterns of excited energy levels.
And how do we know experimentally what shape a nucleus has, especially if it's deformed in its ground state?
A key experimental probe is the electric quadrupole moment, Q. Since this measures the distribution of electric charge, primarily the protons, it gives direct information about the shape of the proton distribution. A nucleus that is intrinsically deformed will have a non-zero quadrupole moment. Generally, a positive intrinsic quadrupole moment, Q arrow, corresponds to a prolate shape, and a negative one, Q arrow, corresponds to an oblate shape. Other probes include the energies of rotational states and the rates of electromagnetic transitions between them.
Why would a nucleus deform in the first place? Wouldn't the surface tension of the liquid drop always prefer a sphere to minimize surface area?
That's a great question. The liquid drop part does favor sphericity, but the shell structure plays a crucial role here too. Remember how the single particle energy levels depend on the potential? Well, the shape of the potential changes as the nucleus deforms. As you deform a nucleus, the single particle energy levels shift and split. For nuclei, with nucleon numbers away from the magic numbers, deforming the nucleus can sometimes rearrange these energy levels in such a way that the occupied levels bunch together more closely near the Fermi surface, lowering the total energy compared to the spherical configuration. This energy lowering, due to shell effects, can overcome the liquid drop's preference for sphericity. The crucial quantity is the shell correction energy, the difference between the actual shell model energy sum and the smooth liquid drop energy. This shell correction depends strongly on deformation and can create energy minima in non-spherical shapes.
So shell effects drive deformation away from magic numbers. What shapes are most commonly seen? Prolate or oblate?
Experimentally, most nuclei that are significantly deformed in their ground state are found to be prolate, the elongated football shape. It seems that for many combinations of protons and neutrons, the shell structure conspires to favor this shape.
But oblate shapes exist too.
Oh yes, oblate flattened shapes do exist, although they seem less common for ground states. The sources mention carbon-12 as an example, and certain isotopes of mercury near Z82 show interesting behavior. In fact, the mercury isotopes around mass 180-190 are famous examples of shape coexistence, where states corresponding to both near-spherical and well-deformed, sometimes prolate, sometimes oblate, shapes exist at very similar, relatively low excitation energies within the same nucleus. The nucleus can sort of flip between shapes.
Shape coexistence, interesting. How do theorists map this out?
They calculate the nucleus's total potential energy as a function of deformation parameters, like quadrupole, elongation, and flattening. This creates a multidimensional landscape called the deformation energy surface. You can calculate this using methods like the macroscopic-microscopic method, which combines the smooth liquid drop energy with the calculated shell correction energy. The minima on this surface correspond to stable or metastable shapes, and the ridges or saddle points represent the energy barriers between different shapes. These barriers are crucial for understanding processes like nuclear fission.
Okay, let's switch gears slightly from structure to dynamics. What happens when nuclei are unstable or in an excited state? How do they change?
Right. They undergo nuclear decay, which is also known as radioactivity if it's a spontaneous decay of the ground state, or they can undergo nuclear reactions if they interact with other particles or photons. Many nuclei, especially those far from the valley of stability, have finite lifetimes and decay spontaneously. And nuclei in excited energy states will almost always decay rapidly to lower energy states, usually by emitting particles or gamma rays.
Alpha decay is one common type of spontaneous decay for heavy nuclei. How does that work? It seems weird that a chunk of the nucleus can just fly out.
It is pretty amazing. Alpha decay is the emission of an alpha particle, which, as we said, is essentially a helium nucleus, 2 protons and 2 neutrons, very tightly bound. The really cool physics here, and the reason it can happen even when energetically it seems slightly blocked, is quantum mechanical tunneling.
Tunneling again.
Yes. The idea is that an alpha particle can preform, at least momentarily, inside the heavy nucleus. But it finds itself trapped behind the Coulomb barrier, the strong electrical repulsion from all the other protons in the remaining nucleus. Classically, if the alpha particle's energy is less than the height of that barrier, it should be stuck inside forever.
But it gets out.
But quantum mechanics allows it to tunnel through that barrier, even though it doesn't classically have enough energy to go over it. There's a small but non-zero probability of finding the alpha particle outside the barrier. This was first explained successfully by George Gamow and independently by Gurney and Condon back in 1928, one of the very first triumphs of quantum mechanics applied to nuclei.
So the gamma theory describes this tunneling probability.
Essentially, yes. The decay rate, or probability per unit time, has 2 main parts. There's a gamma factor, which is an exponential term that represents the probability of penetrating the barrier. It depends very sensitively on the height and width of the barrier, and thus on the energy released in the decay, the Q value. Higher energy means a thinner barrier and much, much faster decay.
And the other part?
The other part is a pre-exponential factor. You can think of it loosely as representing the attempt frequency, how often the alpha particle effectively hits the inside wall of the barrier, combined with the probability that an alpha particle is actually formed and present at the nuclear surface, ready to attempt escape.
And the half-life depends hugely on that gamma factor.
Exponentially. A small change in the decay energy can change the half-life by many orders of magnitude because it affects the exponent in the gamma factor. This explains the huge range of observed alpha decay half-lives, from microseconds to billions of years.
Okay, that's spontaneous decay. What about excited nuclei losing energy? You mentioned gamma rays.
Right. That's often through electromagnetic transitions, commonly called gamma decay. An excited nucleus finds itself in a higher energy state and jumps down to a lower energy state by emitting a high-energy photon, a gamma ray, carrying away the energy difference.
Is it just like an atom emitting light?
It's analogous, yes, but the energies involved are typically much higher MeV scale for nuclei versus EV scale for atoms. The process is described quantum mechanically using electric, denoted E, and magnetic, denoted M, multiple operators. These operators represent the interaction between the nucleus's charge and current distribution and the electromagnetic field. They are characterized by their angular momentum rank, like dipole 1, quadrupole 2, etc., and their parity, whether they conserve or change the nucleus's spatial symmetry.
E1, M1, E2, those kinds of labels.
Exactly. Those specify the type of transition, and the rate or probability of emitting a gamma ray of a certain type tells you something important about the nuclear structure change involved. The transition probability, often expressed as B or BM values, depends on the square of the relevant electromagnetic moment, basically. How strongly the nucleus couples to that particular multipole field. We often compare experimental transition rates to simple theoretical benchmarks called single particle estimates or Weisskopf estimates. These estimate the rate you'd expect if the transition involved just one single proton or neutron changing its state in the shell model potential.
And how do experiments compare to those simple estimates?
It varies. Sometimes the agreement is okay, maybe needing an adjustment factor called an effective charge or effective G factor to account for the fact that even a single nucleon moving can drag the other nucleons, the core, along with it slightly, core polarization.
Yeah.
But what's really striking is when you have collective motion.
Collective motion, like the vibrations or rotations you mentioned?
Exactly. If the nucleus is undergoing collective vibration, or especially rotation, if it's a deformed nucleus, the electromagnetic transitions between these collective states can be much, much stronger than the single particle estimates. For example, the BE2 values for transitions between rotational states in well-deformed nuclei can be hundreds or even thousands of times larger than the Weisskopf estimate. This enhancement is directly proportional to the square of the nuclear deformation. It's a clear signature that the entire nucleus is participating collectively in the transition, not just one nucleon changing orbit. Measuring these enhanced BE2 values is one of the primary ways we quantify nuclear deformation.
It's fascinating how the behavior of the whole nucleus, its collective nature, can be so dramatically different from just summing up its individual parts. Okay, let's zoom out even further now. We've talked about the structure, the forces, the shapes, and how nuclei behave individually or decay. But where do the elements themselves, the atoms that make up literally everything around us, you, me, the planet, where do they actually come from?
Ah, that's one of the grand questions, linking nuclear physics directly to astrophysics and cosmology. It's a fantastic story.
It doesn't all just happen in stars, right? I remember reading the very first elements were made much earlier.
Correct. You're thinking of Big Bang nucleosynthesis, or BBN. In the first few minutes after the Big Bang, the universe was incredibly hot and dense, like a primordial nuclear reactor. In that short window, almost all the hydrogen and helium in the universe was formed, along with trace amounts of deuterium, helium-3, and lithium-7.
Just the very lightest elements, why did it stop there?
It essentially stopped very quickly, mainly because the universe was expanding and cooling rapidly, but also there's a crucial bottleneck. There are no stable nuclei with a mass number of 5 or 8. Once you make helium-4, mass 4, adding a proton or neutron gives you something unstable. Trying to fuse 2 helium-4 nuclei gives you beryllium-8, which is extremely unstable and breaks apart almost instantly back into 2 helium-4s. This mass 8 gap effectively prevented the rapid buildup of heavier elements during the brief BBN era.
Okay, so the Big Bang gave us mostly hydrogen and helium, so everything else, carbon, oxygen, iron, gold, had to be made later.
Yes. The cosmic furnaces where the heavier elements are forged are stars. Through various nuclear fusion reactions happening in the incredibly hot and dense cores of stars over billions of years, processes like the proton chain that powers our sun, or the CNO cycle in more massive stars, and later stages involving helium burning, carbon burning, oxygen burning, silicon burning.
Wow, a whole sequence.
A whole sequence, yes.
Mm.
Stars fuse lighter elements into progressively heavier ones, releasing energy as they climb up that binding energy curve we discussed earlier. This stellar nucleosynthesis is responsible for creating most of the elements up to iron and nickel, around mass 5662, the peak of the binding energy curve.
But since iron is the peak of stability, how do you create elements heavier than that? Fusion stops being energy releasing then, right?
Exactly. Fusing elements beyond the iron peak requires energy input. It doesn't release energy. So stars can't make them through standard fusion burning. That requires different processes, primarily involving the capture of neutrons, which don't face a Coulomb barrier.
Neutron capture. Okay, how does that work?
There are two main processes. First is the SES process, where IDSIS stands for slow. This occurs in the later stages of evolution of stars like red giants. Neutrons are produced relatively slowly, so when a nucleus captures a neutron, it usually has plenty of time to undergo beta decay, if it's unstable, before capturing another neutron. Beta decay changes a neutron into a proton, moving the nucleus up one step in atomic number. So the S process builds heavier elements step by step, sort of meandering along near the valley of stable isotopes on the nuclear chart. It's responsible for producing a significant fraction of the elements heavier than iron, up to about bismuth, mass 209.
Okay, that's the slow path. What about the really heavy elements like lead, gold, uranium?
Those are thought to be primarily made in the R process, where R stands for rapid. This requires an environment with an absolutely enormous density of free neutrons conditions, so extreme that nuclei are bombarded with neutrons and capture them very quickly, much faster than they can beta decay.
Where do you find conditions like that?
The exact astrophysical sites are still debated and actively researched, but the leading candidates are explosive events like core collapse supernovae, the explosions of massive stars, or perhaps the mergers of two neutron stars. In these cataclysms, you get this incredible flood of neutrons. Nuclei capture neutron after neutron, getting pushed way out to the very neutron-rich, unstable side of the nuclear chart.
Far from stability.
Very far. They become extremely heavy and neutron-rich very quickly. Then, once the neutron flood subsides, these highly unstable nuclei undergo a cascade of beta decays, converting neutrons back into protons, moving back towards the valley of stability, but now at much higher mass numbers. This rapid capture, followed by decay, populates the chart with the heaviest elements, including all the way up to uranium and thorium. The sources we had specifically mentioned the R process as the likely origin of elements like uranium, and just to round it out, there are other more specialized processes too. There's the R process, rapid proton capture, which happens in explosive events on the surfaces of neutron stars or white dwarfs, creating some proton-rich nuclei up to mass numbers around 100. And the P process, or gamma process, which involves photons knocking out neutrons or protons from existing heavy nuclei, responsible for producing certain rare, stable, neutron-deficient isotopes called P nuclei. Even neutrinos streaming out of supernovae are now thought to play a non-negligible role in tweaking the final abundances of some elements. It's a complex tapestry of processes.
It truly is mind-blowing to think that the atoms in your hand, the gold in a ring, the calcium in your bones were forged in these incredibly specific, often violent cosmic events millions or billions of years ago, all governed by the fundamental rules of the tiny nucleus we've been discussing.
Absolutely. We've taken quite a journey today, haven't we? From the basic constituents, protons and neutrons that aren't even simple points themselves, and the quirky, complex forces that bind them.
Right, the strong force, weak force,
And
electromagnetism.
through the bulk properties of the nucleus as a whole, hinting at a liquid drop, its different potential shapes driven by shell effects, how it decays via bizarre quantum tunneling or collective electromagnetic transitions, and ultimately how these fundamental processes happening at the femtometer scale dictate the properties of matter we see around us, enable potential energy sources like fission and fusion, and literally built the entire chemical inventory of the universe element by element.
It really highlights that incredible interplay, how the simple liquid drop idea gives way to the much richer structure and rules of the shell model, the absolutely critical role of those leftover residual interactions like pairing, and how even the overall shape of this microscopic object is intimately tied to its internal quantum mechanics, all governed at the end of the day by that peculiar nuclear force.
It's a perfect example of a microcosm that profoundly shapes the macrocosm. The physics inside the nucleus echoes through the cosmos.
And maybe that's the real takeaway for you, the listener, isn't it? That studying these fundamental particles and forces at the smallest imaginable scales isn't just about understanding the infinitesimally small, it continues to unlock the secrets of the most dramatic events and structures in the cosmos. It provides a direct, tangible line connecting the quantum world inside the atom to stellar explosions, the evolution of galaxies, and the history of everything. It makes you wonder, what other cosmic mysteries might nuclear physics be holding the key to unlocking next?